Hi guys, this is the EdExcel AS level sample paper 2 which covers the Further Statistics 1 module. So let's get straight into it. Question number 1. We have over here a university foreign language department which carried out a survey of prospective students to find out which of 3 languages they were most interested in studying. A random sample of 150 prospective students gave the following results. We see the results in this table. A test is carried out at the 1% level of significance to determine whether or not there is an association between gender and choice of language. For part A, we have to state the null hypothesis for this test. So we have the null hypothesis H0. There is no association between language and gender. And just as an added benefit, I thought it would be a good idea to state the alternate hypothesis H1. There is an association between language and gender. So for part B, we have to show that the expected frequency for females choosing Spanish is 30.6. Well, we have this definition for the expected value. We have the expected value, which is equal to the row total times the column total all over the grand total. So with this table over here, we would now need to find out the column totals and the row totals. So for the column totals, 23 plus 38, that's 61. We'll do this in a different colour, we have 61 here. 22 plus 32, that's 54. 20 plus 15, that's 35. 23 plus 22 plus 20, that would be 65. And 38 plus 32 plus 15, that would be 85. And the grand total would be 65 plus 85, which is 150. So we have the grand total, which is 150. Let's just box it. So that's our grand total, 150. So when we come to work out the expected frequency for females choosing Spanish, we have female, Spanish, we're looking at this over here, where this 32 is. The observed value is 32. We want to find out the expected value. So therefore, what we have over here is our row total. Our row total for female, that would be 85. And then we multiply this by our column total. Our column total for Spanish, that would be 54. Okay, and then we divide this by the grand total. The grand total, we said, was 150. So let's work this out on our calculator. We have 85 times 54 divided by 150, which is 30.6. So that's our expected value. Okay? And what we can now do is add that into this table over here. So we have our expected value, 30.6. Okay, so now for part C, we have to calculate the test statistics for this test, stating the expected frequency you have used. So, first of all, the test statistic is given the following definition. So for part C, our test statistic, chi-squared, that's equal to the sum of the observed values minus the expected values, all squared, all over the expected values. Okay? And if you go to the formula book, you'd find that definition given over here. Let's just highlight that, we have this formula over here. So what we need to do is find out the expected values for each of these different cells. So for male French, what we have over here, if I move the calculator here, we have 61 times by 65, so we have 61 times 65 divided by 150, we get a value of 26.43, etc. So we have 26.4, etc. Okay, so let's store these values into our calculator. So let's store this into it. Next, for male Spanish, we have 54 times by 65 divided by 150. You'd find this to be 23.4. So let's store this to B. For male Mandarin, we have 35 times by 65 all over 150. It turns out we get 15.1, etc. So let's store this to C. For female French, we have 61 times by 85 divided by 150, which is 34.5, etc. So here we have 34.5, etc. So we'll store that into D. Next, we have female Spanish. We've already worked that out, but let's just store that into our calculator. So let's store this into E. And finally, female Mandarin, we have 35 times by 85 divided by 150, which is 19.8, etc. So we have 19.8, etc. Let's store this into F. Okay, so now we can work out this value over here of the test statistic. So we're adding all together these values. So adding these together, here we have 23 minus 26.4, etc. over 20 all squared over 26.4. So let's write that down. We have 23 minus 26.4, etc. all squared over the 26.4, etc. And then we add on the next value, which is 22 minus 23.4 squared over the 23.4. Next value, we have 20 minus 15.16, etc. all squared over 15.16, etc. So that was this value over here. For consistency, actually, let's just write 15.1. For the next value, we have 38 minus 34.5, etc. all squared over 34.5, etc. Next value, we have 32 minus 30.6 all squared over 30.6. Next value, we have 15 minus 19.83, 8, etc. all squared all over 19.8, etc. So working this out over here, we end up with a value if we work all this out on our calculator. So we have 23 minus a all squared over a, and then we have the next one, which is 22. So we have 22 minus b all squared over b, and then we have the next one, which is this one here, the 20 minus c all squared over c. For the next one, which is this one, we have 38 minus d all squared over d. For the next one, which is over here, we have 32 minus e all squared over e. So that's this one, and then finally we have the 15 minus the f all squared over f. Okay, so it turns out we get a value of 3.65, etc. So that's our test statistic. Okay, and we've also stated the expected frequencies we've used. We did that in blue over here. Okay, so let's just underline this. So we've already done that. Now for part D, we have to state whether or not the null hypothesis is rejected, justify your answer. So the next thing we need to do is work out the degree of freedom. So for part D, the degree of freedom, that's equal to the number of rows minus 1 times by the number of columns minus 1. Okay, so we have the rows minus 1 times by the number of columns minus 1. So we have how many rows? We have 2 rows, and then we have 3 columns. So our degree of freedom is equal to 2. And we were told in the question that we're looking at the 1% level of significance. So alpha, which is equal to 1%, or in other words 0.01. With this we can find out our critical values. Okay, so we have the degree of freedom, which is 2, and then we have the level of significance, 0.01. So the critical value we can find in the formula book. Okay, so if you go to the formula book somewhere, it's over here. We have here the degree of freedom, which is 2, the level of significance, which is 0.01, and therefore the critical value would be the 9.210. So we have 9.210 as our critical value. So drawing a quick diagram to illustrate this, like so, we have something looking like this. We have our critical value over here. This shaded region is where we reject H0, and here is where we accept H0. So we have our critical value being 9.210. We've just found our value over here to be 3.65. 3.65, that goes here somewhere. So here we have 3.6, etc. So we're in the region where we accept H0, and therefore, because of that, we can conclude that the null hypothesis is not rejected. Okay. Now for part E of the question, we have to explain whether or not the null hypothesis would be rejected if the test statistic was carried out at the 10% level of significance. So this time, alpha is equal to, for part E, alpha is equal to 10%, which is equal to 0.1. Okay, so we can find out our critical value. So our critical value, if we go over here, we still have, if we use a different color, we're still using this over here, and then this time we're looking at the 10% level of significance, so the corresponding value is over here, the 4.605, etc. So we have here 4.605. So again, drawing this diagram out again, so we have our critical value 4.605 here, and then obviously this value of 3.6, etc. is still below this critical value, and therefore we can see that the null hypothesis is not rejected. Let's just write that down. So we see that the null hypothesis is not rejected again. Okay, so that's question 1 done. Question number 2, we have over here the discrete random variable x, which has a probability distribution given by this table over here. So we have x values, and then we have the probability that x equals x shown in this row over here. And the random variable y equals 2 minus 5x, and given that the expected value of y is equal to minus 4, and that the probability that y is greater or equal to minus 3 is equal to 0.45, we have to find the probability distribution of x. So what this suggests to us, we need to find out the values of a, b and c, and then doing that we would have found the probability distribution. Okay, so for part A, we have y, which is equal to 2 minus 5x. Okay, so the expected value of y, substituting in, we're looking at the expected value of 2 minus 5x. And what we have over here we can rewrite as 2 minus 5 lots of the expected value of x. I assume you're all familiar with this. And we know that this expected value of y is equal to minus 4. So this over here is equal to minus 4. Okay? So hopefully that makes complete sense what I've said there. Okay? So knowing that, we can now solve for the expected value of x, and hopefully you can see the expected value of x. Well, if we add 2 to both sides and then divide by minus 5, we have over here minus 4 minus 2, and then dividing this by minus 5, we end up with 1.2. So the expected value of x is equal to 1.2. Okay, now what does this mean? Well, it means that if we multiply x by the probability of x equaling x, we'd get 1.2. So in other words, the expected value of x, that's equal to the sum of the x's times by the probability that x is equal to x. Okay, so using what we have over here then, if we multiply those together, just underline this, we have minus 1 times by c, okay, and then we have 0 times by a, and then we have 1 times by a, and then we have 2 times by b, and then we have 3 times by c. And we know that all this is equal to 1.2. Okay, so because the expected value is equal to 1.2, this thing is equal to 1.2. Okay, so what we can now do from here is form an equation. We have a plus 2b plus 2c equals 1.2. We'll call this equation 1. What else we know is that the probability that y being greater or equal to minus 3 is equal to 0.45. So we have the probability that y is greater or equal to minus 3 being the same as the probability that 2 minus 5x being greater or equal to minus 3, and we know that this is equal to the 0.45. Well, if we tidy this up a bit, so if I subtract 2 from both sides, we have minus 5, this is minus 5x. So we have 2 minus 5x rather. So we have 2 minus 5x being less than or equal to minus 3. So we see that x is less than or equal to, we have 2 minus 5x being greater or equal to minus 3. So we see that x is less than or equal to minus 1. Okay, so with this, we know that all this is equal to 0.45. So this over here is equal to 0.45 because we were told in the question over here. Okay, so anything that's less than 0.45, what we have over here then is anything that's less than or equal to minus 1. So we have minus 1, 0 and 1. So what this is the same as is the probability that x is equal to minus 1 plus the probability that x is equal to 0 plus the probability that x is equal to 1. So hopefully if I change this colour, hopefully you can see that this over here is the same as what we have over here. And this of course is equal to 0.45. So the probability that x is equal to minus 1, that's equal to c. And then we have the probability that x equals 0, that's a. And what we also have is the probability that x is equal to 1, that's a as well. And this is equal to 0.45. So what we can see then, our second equation, we have 2a plus 0b plus c, that's equal to 0.45. Okay, hopefully that's straightforward so far. And the last thing you should know is that the sum of probabilities is equal to 1. Okay, so adding all these probabilities together, we have c plus a plus a plus b plus c. Okay, so let's just write that down. We have c plus a plus A plus B plus C equals 1. So in conclusion, we have 2A plus B plus 2C equals 1. So if I call this equation 2 and this equation 3, what we can now do is form a matrix system to solve equation 1, 2 and 3 simultaneously. Let's just write that down. So if we form a matrix system, well, the coefficients, well, the first equation over here, we have A plus 2B plus C. So we have 1, 2, 2. The second equation, we have 2, 0, 1. So we have 2, 0, 1. And the third equation, we have 2, 1, 2. Alright? And then we multiply this by A, B, and C. And this is equal to 1.2, 0.45, and 1. So you may know this from your core pure knowledge. Alright, so A, B, C, that's equal to the inverse of this. So we have 1, 2, 2, 2, 0, 1, 2, 1, 2, inverted, multiplied by 1.2, 0.45, and 1. So working this out, what we end up with over here then is, if we go to our calculator, let's go to the, well, we can solve this simultaneous equation using our calculator as well. So we have 1, 2, 2 and 1.2, and then we have 2, 0, 1, 0.45, and then we have 2, 1, 2, 1. Oh, I wasn't meant to press that. So we have 1, 2, 2, 1.2, 2, 0, 1, 0.45, and then we have 2, 1, 2, and 1. So we see that A is equal to 0.1, B is equal to 0.3, and C is equal to 0.25. Okay, so we can conclude over here, A is equal to 0.1, B is equal to 0.3, and C, that's equal to 0.25. Okay, so let's just fill these values in. We have A, which is 0.1, so we have 0.1 here, 0.1 here. We have B, which is 0.3, so we have 0.3 here, and then we have C, which is equal to 0.25, so we have 0.25 here and 0.25 here. Okay, so now for part B, given that also the expected value of y squared is equal to 75, we have to find the exact value of the variance of x. Well, we can use this information over here to find out the variance of y, and we also know the expected value of y. So those are related through the following way. So for part B, the variance of y, that's equal to the expected value of y squared minus the expected value of y all squared. Okay, so the expected value of y squared, this over here, that's equal to this 75. So we have 75 minus 4 all squared, and remember this is the value of the expected value of y, as we said over here, and working this out, of course, will come out with 59. Okay, so the variance of y, that's equal to 59, and we already know what y is. We were told y, that's equal to 2 minus 5x. So the variance of 2 minus 5x, well, of course, that's just the same as 5 squared times by the variance of x. And we know that this, of course, is equal to 59. The reason being, if we get a different colour, the reason being is the variance of y, which is the same as this over here, is equal to 59. So in conclusion, we can see that the variance of x, that's equal to 59 divided by 5 squared, which is 2.36. Okay, so that's part B done. And now for part C, find the probability that y is greater than x. Okay, so now for part C, we have to find the probability that y is greater than x. So this is the same as the probability that 2 minus 5x is greater than x. And if we rearrange over here, well, solving for x, so add 5x to both sides, so we have 2 being greater than 6x, and then dividing by 6, we see that x is less than 1/3. So the probability that x is less than 1/3, we have x equals -1 and x equals 0. Okay, so we have here the probability that x is equal to -1 plus the probability that x is equal to 0. So just to confirm, this over here is the same as what we have over here. Okay, so the probability that x is equal to -1, that's equal to C, and the probability that x is equal to 0, that's equal to A. So here we have C plus A, which is 0.1 plus 0.25, which is equal to 0.35. Okay. Question number 3. 2 car hire companies hire cars independently of each other. Car hire A hires cars at a rate of 2.6 cars per hour. Car hire B hires cars at a rate of 1.2 cars per hour. In a 1 hour period for part A, we have to find the probability that each company hires exactly 2 cars. Okay, so for this question, what you have to recognize is we have to use a Poisson distribution, okay, because we've got rates over here, and the 2 car hire companies hire cars independently of each other. So using a Poisson distribution, if we call this x over here has a Poisson distribution with parameter 2.6, and for this one, y has a Poisson distribution with parameter 1.2. So what we're looking at over here is the probability that each company hires exactly 2 cars. So we're looking at x equaling 2 and y equaling 2. The reason for that is because we were told over here we're looking at each company hiring exactly 2 cars. So we're looking at over here for part A, the probability that x equals 2 and the probability that y equals 2. Okay, so the probability that x equals 2, we can do all this on the calculator. So going to the Poisson PD section, with a variable we have x equaling 2 with lambda equaling 2.6. So we have 0.251, etc. So let's store this into A. And we also have over here 1.2. So we multiply this by 0.216, etc. So let's store this into B. And multiplying those together, so we have A times by B, which is 0.0544. 4, etc. Now for part B, in a 1 hour period, we have to find the probability that the total number of cars hired by the two companies is 3. So we're looking at over here the total number of cars hired by the two companies. Okay, so what we'd have to do therefore is add these together. And what we're looking for is x plus y equaling 3. The reason we have this equals 3 is because we're looking at the total equaling 3 still in this 1 hour period. Okay, and if you notice over here, here we have per hour and here we have per hour. So we can still look over here in this 1 hour period. We'll just have to add those probabilities together. So what we have over here then is well, first of all, what we need to look over here at is the following. We have the x plus the y having a Poisson distribution with parameter 2.6 plus 1.2, which is 3.8. Okay, so working this out when x is equal to 3, so let's go back here. So we have x equaling 3, our parameter here is 3.8. Working this out, we end up with 0.204, etc. Now for part C, what we have over here is in a 2 hour period, so that's a bit interesting. We've got this time a 2 hour period. We have to find the probability that the total number of cars hired by the two companies is less than 9. Okay, so first of all, we have to work out our new rate. Let's just write this down. So we've got A, which hires at a rate of 2 times by 2.6. Now, the reason we have to multiply by 2 is because this time, here, well, we were told here we have 2.6 cars per hour. So in a 2 hour period, we'd have to multiply by 2. And the same thing with B. And if you look over here, we're looking at the total number. So because we're looking at the total number, we'll call this Z. Z has a Poisson distribution of 5.2 plus 2.4, which is 7.6. Okay, so we'd have to add those together to give the total. And we're looking at over here the probability that Z is less than 9. And this is the same as the probability that Z is less than or equal to 8. So working this out, so here, this time, still using our distribution, we've got a Poisson cumulative distribution. We have a variable, so we have 8 over here and 7.6. So working that out, we come out with 0.648, etc. Okay. Now for part D of the question, on average, 1 in 250 new cars produced at a factory has a defect. In a random sample of 600 new cars produced at the factory, we have to find the mean number of cars with a defect, and we have to find the variance of the number of cars with a defect. Well, obviously here we'd have to use a binomial distribution for the following reason. So we'd have to use a binomial distribution because we have n identical trials which are independent. We've got n equaling 600 obviously, because we're taking that much of a sample, and we've only got 2 outcomes, defect or no defect. So the first thing we can say from here is we've got C, which is binomially distributed with parameter 600, and the probability that we've got a defect, that's 1 in 250. Okay, so for the first part, when we come to find the mean of a binomial distribution, if you go to the formula book somewhere, the mean of a binomial distribution, let's grab a highlighter, that's given by this over here, and the variance is given by this over here. So we have the mean NP, that's equal to 600 times by 1 over 250, which is 2.4, and the variance, so the variance, that's equal to NP lots of 1 minus P, so we have 600 times by 1 over 250 times by 1 minus 1 over 250. And if we work this out, so we have 600 times by 1 over 250 times by 1 minus 1 over 250. So we end up with 2.3904. So we have 2.3904. Okay. For the next part, for part E, we have to use a Poisson approximation to find the probability that no more than 4 of the cars in the sample have a defect, and then give a reason to support the use of a Poisson approximation. So here we're using the Poisson approximation for the binomial distribution, and what we have over here is the mean, which is 2.4. So for part E, we've got D, which follows a Poisson distribution with parameter 2.4, and the reason it's 2.4 is because that's what we worked out the mean to be. Okay. And having said that, we're looking at the probability that D is less than or equal to 4, and the reason we're doing that is because we were told in the question no more than 4. So let's just highlight this perhaps. So we have no more than 4. So we've got this over here. And working this out, well, what we'd have to do is go to the distribution section. We have a Poisson cumulative distribution. So x is equal to 4 and lambda is equal to 2.4. So working this out, we end up with 0.9041, etc. And for the next part, we have to justify our use of why the Poisson approximation was used for the binomial. So we have the following reason. So we've got n, which is large, so we've got a sample of 600, so n is large. The probability is small, p is equal to 1 over 250, and the mean is approximately equal to the variance. You saw that over here. The 2.4 is approximately almost the same as the 2.3904. So that's why we can use the Poisson distribution. So therefore the Poisson model is suitable. Okay. Question number 4. The discrete random variable x follows a Poisson distribution with mean 1.4. For part A, for the first part, we have to write down the value of x equals 1. Okay. So for part A, we've got x which follows a Poisson distribution with mean 1.4, and for the first part we're looking at the probability that x is equal to 1. Okay, so go to our distribution section. We have a Poisson PD variable, x is equal to 1, the mean is equal to 1.4, so we end up with 0.345, etc. For the next part, we're looking at the probability that x is less than or equal to 4. So working this out, this time we'd have to use the Poisson CD. We have variable, so we have x equaling 4 this time. So we end up with 0.985, etc. Okay, so that's part A done. For part B, the manager of a bank recorded the number of mortgages approved each week over a 40-week period, and that's shown in that table here, and we have to show that the mean number of mortgages approved over the 40-week period is 1.4. So over here we just have to multiply the number of mortgages approved by the frequency, and then we divide by the total of the frequency. So all this is a case of is it's just a case of it's nothing more difficult than what you'd find at GCSE. So I'll write down all the working out over here, and then we can just stick it into our calculator. So we've got over here the 0 times by the 10, the 1 plus the 16, the 2 times by the 7, etc. all the way up to 6 times by the 1. That's on the top line, and on the bottom line we just add up all the frequencies as over here. And if you work this out, you get 1.4. And just in case you want to do that on your calculator, all we have to do is go to the statistics menu. Number 1, well, we need to turn on the frequency. So frequency on. So we have 0, 1, 2, 3, 4, 5, and 6. And the frequencies are 10, 16, 7, 4, 2, 0, 1. And if we work out the variable calc, well, you'd see the mean over here is equal to 1.4. And then obviously we've got the other summary statistics. Okay, so that might be quite useful to do on your calculator, just in case you don't know how to do it. Now for part C, the bank manager believes that the Poisson distribution may be a good model for the number of mortgages approved each week. She uses a Poisson distribution with a mean of 1.4 to calculate the expected frequencies as follows. So we've got the number of mortgages approved, and then we've got the expected frequencies shown here. We have to find the value of R and the value of S, giving an answer to 2 decimal places. Okay, so for this question, what we can do over here is create a new table. First of all, you'd have to recognize here we've got 5 or more. Okay, so what you'd find over here, if we add all these together, we can find out the total number of observations. So we've got 10 plus the 16 plus the 7 plus the 4 plus the 2 plus 0 plus 1. We come out with 40. So for part C, the total number of observations, n, that's equal to 40. We have our mean equaling 1.4, and obviously it follows a Poisson distribution. So what we can now do is create a table. So we've got our x values, which is the number of mortgages approved. So we have 1, 2, 3, 4, and then 5 or more. So we have 0, 1, 2, 3, 4, and then 5 or more. So we have 5 or more, like that. And then we can find out our frequency. Okay, so over here what we've got is expected frequency, so the observed frequency, or I. We have 10, 16, 10, 16, 7, 4, 2, and then for the rest of them, for 5 or more, we have 0 plus 1, which is 1. Okay, and then we've got our expected values as well. So we've got EI. Now I will give the values of EI to the way we find EI actually is we need to find out the probabilities first of all. So before that, we can find out the probability that x equals xi. Okay, so we can do this on our calculator. It's quite a straightforward thing to do. So go to the distribution section. We have a Poisson PD list. So the first thing I recommend you do is look at the original table over here. So we've got 0, 1, 2, 3, 4, 5, 6. Our mean is equal to 1.4. So actually a better way of doing this. Can I delete values here? So we're looking at 5 or more, so let's delete this. So let's just go up to 4 for now, and then for 5 or more we'll do 1 minus all that. So working this out, we have 0.2466. We'll put this to 4 decimal places for now. So here we have 0.2466, and what we'll do as well, we'll store these values. So we'll store this into A. For the next one we have 0.3452, so we'll store this into B. For the next one we have 0.2417. We'll store this into C. For the next one we have 0.1128. So we'll store this into D. And then for the next one, we have 0.03 or 0.0395. So we'll store this into E. So let's store this into E. Alright, so for 5 or more we can figure out that probability. So to do that, we'll do 1 minus the others. So we have 1 minus A minus B minus C minus D minus E. So we end up with 0.0143. Okay, and we know that n is equal to 40. So what we'll do is we'll store this into F. So we will now store this into F, and we will multiply each of these by 40. Okay, so what we will now do is calculate EI. Okay, so doing that we have 40A, which is 9.863. We'll put it to 4 decimal places, so we have 9.8639. For the next one, we have 40 times by B, so we have 13.8094. So we have 8094. And then for the next one we have 40 times by C, which is 9.6666. Then we have 40 times by D, which is 4.5111. And then for the next one, 40 times by E, we end up with 1.5789. And then for the next one, we've got this times by F, and this one is 0.57 or 1. Okay, so in conclusion, what you can hopefully see then is we have to state the value of R and S. So R is equal to what we have over here, the 13.81. So R is equal to 13.81 and S is equal to 0.57, both to 2 decimal places. Okay, so that's that done. Now what we can do for part D is, well, the bank manager will test at the 5% level of significance whether or not the data can be modelled by a Poisson distribution. We have to calculate the test statistics and state the conclusion for this test, state clearly the degrees of freedom and the hypotheses used in this test. Okay, so what we have over here for part D is alpha being 5%, so we have 0.05. What we can do over here as well is, well, we have to recreate this table. We'd have to combine these last three cells, because these together, each of these is less than 5, so we have to combine those. Let's actually write that down, that's actually quite important. So that's what we'd have to do, we have to combine these cells. So what we'll do is we'll copy and paste this table. So let's just copy and we'll paste it here somewhere. So what you'd have to recognize is we'd have to combine the last couple of entries, which are less than 5. So over here we'll do 3 or greater. So for that, what we'd have to do over here is we'd have to, well, so let's add these together. So we have A, B, C, D, E, F. So let's add those together. So we have D plus E plus F. So we end up with over here the 0.166, etc. So essentially what I'm saying over here is, well, 4 plus 2 plus 1, that would be 7. So let's just get rid of all this. Here we have 7, so we don't need these as well. And this over here is equal to these 3 added together, which I've just rubbed out, that's equal to 0.1665. And if I multiply that by 40, we end up with these 3 added together, which is, if I quickly work that out, we have over here 6.6601. Okay, so we had to combine those. Okay, so hopefully that makes sense. And what we can now do is, now that we've calculated that, well, let's store this into D. So let's store this into D. What we can now do is state our hypotheses. Alright, I'll quickly write those down. So for our hypotheses, we've got our null hypothesis. The Poisson distribution is suitable. Remember, if you go back to the question, we're looking at whether or not the data can be modelled by a Poisson distribution. And the actually, let's highlight that. So over here, the reason we've got these hypotheses for our alternate hypothesis as well, we've got the Poisson distribution is not suitable. The reason for that is because we're looking at the bank manager is testing whether or not the data can be modelled by a Poisson distribution. Okay, so having done that, we can now calculate our degrees of freedom. Our degrees of freedom will be the number of cells minus 2. And the reason we subtract 2 over here is because we're using a, well, I'll write it down. The reason we subtracted subtracting to is our mean is estimated by calculation. Okay, so that's why we'd have to subtract 2. Alright, so you should be familiar with that. And we know that we estimated the mean because over here, that's what we had to do over here. We had to calculate the mean over a 42-week period. So that's why we'd subtract 2. So the degrees of freedom, well, we have over here 1, 2, 3, 4 cells minus the 2. The degree of freedom is equal to 2. Okay? So what we can now do is work out our test statistics. So before we do that, remember our test statistic, that's equal to OI minus EI all squared over EI. Okay, so we'd have to calculate that. So we have over here OI minus EI all squared all over EI. So what we'd have to do over here then is, if we calculate that, actually let's get rid of this. Let's just get rid of, we'll just work it out straight away. So what we have over here then is we can work this value out easily. So here we have here we have chi squared, which is equal to this. So what we have over here is 10 minus the 9.8 etc. all squared over the 9.8 etc. And then we have 16 minus 13.8 etc. squared over 13.8 etc. And then we have 7 minus 9.6 etc. all squared over 9.6 etc. And finally we have over here 7 minus 6.6 etc. all squared over the 6.6 etc. So working out our test statistic is, well, what we'll do over here is, well, we have A, which is this, and then we multiply that by 40 to get this. So we'll store this into A, and then the next one we have B times by 40. So now we'll store this into B, and then we have C, and we'll times this by 40, and then we'll store this into C, and then D should already be stored somewhere. Yeah, it is. So working all this out, putting all this into your calculator, so here we have 10 minus A squared over A plus our next one, which is 16 minus B all squared, so B all squared over B. And then for our next one we have 7 minus this C all squared over C. And then for our last one, we have 7 minus D all squared over D. So if I've stored these values correctly, we should come out with 1.1, etc. So we'll write this on the next line. So we have our test statistic, which is equal to 1.1 or 3, etc. So what we can now do is find out our critical value. So we have 2 degrees of freedom, and we're looking at the 5% level of significance. So if we go to our formula book, under the chi-squared section, so that's around here somewhere, we've got 2 degrees of freedom. We're looking at the 5%, so that critical value turns out to be 5.991. So we have 5.991, and now what we can do is draw a quick diagram. So here we have our critical value where we reject H0, and here is where we accept H0. We've got a critical value of 5.991. It turns out we got a value of 1.1 or 3, etc. So we're in the region where we accept H0. So we conclude that we do not reject H0, and because of that we can say in conclusion that the number of mortgages approved each week, so approved each week, follows a Poisson distribution. So follows a Poisson distribution. Okay, so that's the end of the paper. I hope you found this pretty useful. Yeah, so that's the end.